Let's assume we have this function, the voltage equals, as a function of S. Again, how we came up with this, don't worry about it now. Let's say we have 10 times S plus 3 over S plus 1 cubed times S plus 2. Now, if you want to break that, you probably did that in math. We normally break that because by the way, we're looking to find what is VT. That's what the question is. Change it to time. In math, you probably did this. Well, let me write this something over S plus 2 because that's a distinct root. It's not repeated. But the S plus 1 is repeated. So maybe you'll put that over S plus 1 squared, S plus 1 cubed. I don't know if that's how you did it in math. I put 1. It's not a 1. Now we're going to decide what's going to go on the top. Well, since this is linear, which means the linear highest power is 1, the top is always 1 degree lower than that. What is 1 degree less than 1? 0 degrees. So these will have to be constant. So let's give them some value. Let's call them K subscript 1 1. K 1 2. I could call them K1, K2, K3, K4. I don't know why I did that. You know what? I'll do this. I'll call that K, different one. For the repeated roots, I'll change them. I'll go K1 1, the first one of the repeated. K1 2 for the second one. K1 3. I can call them anything. A, B, C, D. It really doesn't matter. But these are the repeated ones, you know. And this is the single one. Now to find K, because that's a simple distinct root like we did last time, that's a straightforward. K is going to be, notice K is sitting on top of S plus 2. What we did last time, we went to this function, we took S plus 2 out of it. We took the S plus 2 out. And you want to find this when S equals what? What value makes the bottom 0? Negative 2. So plug it in. 10 times, what's negative 2 plus 3? That's a 1. What's negative 2 plus 1 is negative 1 cubed. That's a minus 1. That's a negative 10.
Where did the negative 2 come from?
The value that makes the bottom 0.
Right, okay.
Now, K11, go ahead.
Makes the value of the original 0.
Which one here?
K over S plus 2.
Yes.
That's how we decide what makes it 0.
Well, yeah, what makes the bottom 0?
Okay.
The pole.
K11 as
Because
well.
you were looking at the next equation when you said what makes the bottom 0.
Oh, no, we
Makes
take
the
this one
bottom
out.
1. So I was
Yep,
confused.
yeah, this one's 0, yeah. Now K11, notice that's sitting on top of S plus 1. That means you got to take S plus 1, you got to take all of it out. So what's all of it? What's left then? If you take S plus 1 out of the picture, what's left? 10 times S plus 3 over S plus 2. And what makes this value 0? Negative 1. So 10 times, what's negative 1 plus 3?
2.
2. What's negative 1 plus 1? 1. That's 20. Now 1, 2 and 1, 3 will be tricky. Now, so the first one is this one. Now the second one, the squared, it's not going to be the answer to this when s is minus 1. That'll give me the same answer. It's going to be the derivative of this. The derivative of this when s equals negative 1. So you got to take the derivative of that. Then I have to use the quotient rule, right? You have a fraction. And it's what? It's the bottom times the derivative of the top, which is what? 10 minus the top times the derivative of the bottom, which is what? 1 over the bottom squared. Is that what the quotient rule is? When s equals negative 1. If I simplify it, I see the 10s and minus the 10s, they'll disappear. See that? Then I get 20 here, and there's minus 30. That's a negative 10, if I did it right in my head here. If you simplify the top, that's negative 10 over s plus 2 squared. You want to find out when s equals negative 1. So that's negative 10 over negative 1 plus 2, which is what? 1 squared, that's a 1, that's a negative 10. And now let's do the K13. K13, K12 was the derivative. Guess what K13? The second derivative. Which happens to be the derivative of this first derivative, right? It's the derivative of this. I like this one better because I can use the extended power rule. I can rewrite that to negative 2. And to take the derivative of that, we use negative 10 times a minus 2, which is what? 20. Subtract 1 from the power, which is what? Negative 3, times the derivative of what's on the inside, which happens to be a 1. So that's 20 over s plus 2 cubed when s equals negative 1, and that's 20 over 1, and the answer is 20. I think it's quicker than math, the way it did in differential equation. So now we know what K1, K2, and K3. Here we go. K is what? Negative 10. So I can write Vs, which is K, that's a negative 10, over S plus 2, plus K11, which is what? 20, over S plus 1, plus the other one, which is negative 10, S plus 1 squared, and the last one, 20 over S plus 1 cubed.
How does that follow since you used a different s each time you solved it? The first time you solved it.
What do you mean the first time? The first
First time we
time?
used negative 2.
Yeah, because that's the value that makes this one 0.
Right.
And that's the value for all of these. That's what makes the denominator 0. So that's why I have to use a different S for them. Which one, the math?
Yeah.
Yeah, the algebra.
It's derived out, so.
Huh?
Well, we saw it derived out. This one. I thought it's more straightforward because you don't really have to decide anything with this one. Like the other one, like just pick this.
Collect like terms, yep. Group them and all that.
Foiling, like.
Now we got to find the inverse Laplace. Well, the first two, the inverse Laplace, straightforward. What's the first two? What's VT? Isn't that negative 10 e to the minus 2t? That's this one. The other one is what? 20 e to the minus t. Now the other two are a little bit tricky. So let me take a peek here at our Laplace from last time. I put a chart on the board, and you probably have it somewhere. Where's our book? When we did the Laplace, where's that chart? I'm sure we have it in the book. Here we go. I put that chart on the screen last time, and it says if you have 1 over s plus a to the n, then the Laplace of that, the inverse Laplace will be t to the n minus 1 over n minus 1 e to the minus alpha t. So let me write that equation there for you. That's this one. I'll put it in red. The Laplace of t to the n minus 1 over n minus 1 factorial e to the negative alpha t is equal to 1 over s plus alpha to the n power. Or if you want to rewrite it differently, the inverse Laplace of 1 over s plus alpha to the n, and that's what we have, should be t to the n minus 1 over n minus 1 factorial e to the minus alpha t. And that's the equation I'm going to use. So I'm going to look at this. Here's the 10, the negative 10 in the front. I'm looking at this one. This is the inverse Laplace of 1 over s plus 1 squared. So I know alpha is 1 here. See that? Alpha is 1. And what is n, by the way, when you compare the power? N is 2, isn't it? So that would be t to the power 2 minus 1. What's 2 minus 1? 1 over, I can put the 1 here if you want to. N is 2. What's 2 minus 1? 1. What's 1 factorial? Which is still 1. E to the power of negative t. Here's the 20. Let's do this one. For this one, n is 3. So it's going to be t squared divided by 2 factorial e to the power of negative t. And now all I got to do is just clean it, and I got my answer. One factorial is 1, that's negative 10 t e to the negative t. 2 factorial is 2, that would be positive 10 t squared e to the negative t. And usually with all our circuits problem, we say that's really u sub t because we don't build the circuit at t equals minus infinity. We go to the lab and we build it. And when we walk into that lab, that's your time 0. So we always put u sub t there. I'll try another one. I'll take the one in our book. Where's the inverse? Here we go. Let's get an example in our book. I got one. Okay. Let's take this one. That's an easy one. Let me see if I can find a bigger one at the end of the chapter. I mean, I can make any one. But let me take a peek and see if I can find one that has multiple roots, not just one or two.
So this only works for first degree. So
For repeated roots, correct. Second degree is a different story. We're going to be dealing with that shortly. Okay. Boy, oh boy. You want to make it really ugly? Really, really ugly? Now, if I was given this, I'd probably cheat and go back to my math. Do it the other way. Because I'm looking at some ugly one. I'm looking at this. F of s equals 4 over s plus 1 to the 4th, s plus 1 squared. Two sets of repeated roots.
is there a reason why they just left them separated besides?
Yeah, isn't that just s plus 1 to the 6th?
Oh,
The number?
I copied that wrong. I'm sure they're not then s plus 1.
So the
They did actually. Huh. Nope. I did. So let's make one of them, make that the one of them is 4, s plus 4.
So the math way would be faster?
Probably, because you can rewrite that as a over s plus 1 to the 4th plus b over s plus 4 to the 2nd. And once you find a and b, you know what the inverse Laplace of each one. But I'll do them our way. So I'll call one of them 1, and this is 2. So maybe I'll break it down to, let me go a's and b's instead of k. a1 over s plus 1 plus a2 s plus 1 squared plus a3. Do I really want to take the fourth derivative? S plus 1 to the 3rd. How about we just make 3? That's plenty. Otherwise, I'm going to be here the whole day. How about that 3 instead of a 4? You know. And in the bottom, we have b over s plus 4 plus what? Or b1 plus b2 over s plus 4 squared. I can find a and b quickly, or a1 and b1. That's what I meant. So a1, notice a1 is sitting on top of s plus 1. So you go to the original problem, and you take all of s1 plus 1 out. So you have 4 over s plus 4 to what power? Squared. So s plus 1 is gone. When? When s equals what? Negative 1. So 4 over, what's minus 1 plus 4? 3 squared, which is a 9. That's 4 over 9. A2, actually that's not bad. It's the derivative. The derivative of what? 4 over s plus 4 squared. When s equals negative 1. Actually, that's not bad. Taking the derivative is straightforward. Because if I rewrite this problem, it's the derivative of 4 times s plus 4 to what power? Negative 2? And let's take the derivative. That's a negative 8 s plus 4 to what power? Negative 3 times the derivative, what's on the inside, which is a 1. So that's equal to negative 8 over s plus 4 cubed, when s equals negative 1. That's negative 8 over minus 1 plus 4 is 3 to the third power. Is that 27? Negative 8 over 27. A3. A3 is the second derivative of 4 over s plus 4 squared, when s equals negative 1, which is the derivative of the first derivative. The first derivative happens to be negative 8 s plus 4 to the negative 3, and that will give me what? 3 times 8, 24 s plus 4 to the negative 4, s equals negative 1. 24 over s plus 4 to the fourth. This will be 3 to the fourth, and that's 81. Not bad, not bad. Quick. Didn't really take that long yet. We get B1 and B2, then I'm done. B1 again, straightforward. We go to this expression. Notice B1 is sitting on top of s plus 4. We take s plus 4 out of this. Let's see what B1 is. B1, take the s plus 4 out of this expression. You have 4 over s plus 1 to the third. When s equals, what makes the bottom of B1 0?
Negative 4.
Negative 4. That's 4 over, what's negative 4 plus 1? Negative 3, cube it. That's negative 4 over 27. And B2, and I'm done, it's the derivative of 4 over s plus 1 to the third when s equals negative 4. And I can write that the derivative of 4 times s plus 1 to the negative 3 when s equals negative 4. Let's take the derivative now. That's negative 12 s plus 1. Is that negative 4? When s equals negative 4. Or negative 12 over s plus 1 to the fourth power when s equals negative 4. Negative 4, that's negative 12 over 3, negative 3 to the fourth power. Is that 81?
To the third power, I think, was 81.
3 times 3 is 9, times 3, 27, times 3, 81, right? Now I can divide by 3. Negative what? 4 over 27. And I'm done. I found all the values that I need. I know all the constants, A1, A2, A3, B1, B2. Since they're all fraction, maybe I'll put them in the front. We'll look a little bit cleaner. Put them on the next page.
So B2 is just the derivative of B1, correct?
Correct. And if there was cube, like more power here, since this was cube, for example,
Yeah, you just get
then
the derivative.
B3 would be the second derivative, and so forth.
Yeah.
Yeah.
The 4 is coming from the actual original problem.
The 4 is what makes the bottom of this one 0.
Got it, okay.
The negative 4, you mean? Is that what you're asking about? Negative. Yeah. And the other one, we use the -1 because that's the pole that makes the bottom 0. Undefined. So now I can rewrite it on the next page, nice and clean. So f of s, and I'll take these A1. A1 is what? 4 over 9. I'm going to put it in the front because it's ugly there. 4 over 9 times 1 over s plus 1. Plus A2. What's A2? A2 is negative 8 over 27 times 1 over s plus 1 squared. Plus A3, which is 24. I can simplify 24 over 81, right? I can divide by 3. By 3, this is what? 8? Is that 27? If I simplify it. So plus 8 over 27 times 1 over s plus 1 cube. Plus B1 now. Negative 4 over 27 times 1 over s plus 4 plus the last one, which is negative 4 over 27 1 over s plus 4 squared. Now let's take the inverse. Again, the rule I'm going to use, the inverse Laplace of 1 over s plus alpha, that's one of them I'm going to use, is e to the minus alpha t. The other one I'm going to use, the inverse Laplace of 1 over s plus alpha to the n power, is what? T to the n minus 1 over n minus 1 factorial times e to the minus alpha t. Those are the rules I'm going to be using. So there's the 4 over 9, f of t. We use lowercase for the time domain usually. 4 over 9. What is the inverse Laplace of 1 over s plus alpha? E to the minus 1t. This will be minus 8 over 27. Now notice here n is 2. So t to the power of 2 minus 1, which is 1 over 1 factorial, e to the power of negative t. We'll come back and clean it. Plus 8 over 27. That's this one. N is 3. See, n is 3 there, the power? So it's going to be t to the power 3 minus 1, which is 2 over 2 factorial, e to the minus t. Now I'm right here. That's a negative 4 over 27 e to the power of negative 4t. And the last one, it's negative 4 over 27 n is 2 again. N is 2, that's t to the 1 over 1 factorial e to the minus 4t. Little cleaning, then I'm done. This is 8 over 27 t e to the minus t. 8 divided by 2, that's 4 over 27 t squared e to the minus t, minus 4 over 27 e to the minus 4t, minus 4 over 27 t e to the minus 4t. Again, we're probably going to take use of t here in circuit.
Will we be dealing with a lot of like inverse Laplace of like powers like this, like to the fourth?
Well, you could end up with some. I don't know how often you're going to see it, but in case you do, you know. The problem is going to be dealing with probably quadratic equation at the bottom, a couple of simple roots, you know, maybe one repeated root, but we'll see. So this is the inverse Laplace of a repeated root.